Hello, we would like to get started with the next talk. Could you please come back for the talk now?
All right, great. So ready to go with our next presentation. And so let's get started. So really my pleasure to announce our next presentation is Ellie Martin from UCL, who is going to tell us about quantification of acoustic pressure in the brain. So thank you so much, Ellie.
Hi, everyone. Thanks, Kim, for the introduction. So yeah, as Kim said, I'm going to talk about trying to quantify acoustic pressure in the brain during neuromodulation treatments. Okay, sorry, there we go. So yeah, I guess why do we want to know the pressure in the brain? We've had a lot of talks already over the last couple of days about various different studies with completely different setups. So whatever the setup is, whether we're doing something where it's kind of a single go and you're coupling a transducer to a participant, you don't have any imaging or anything like that. Maybe afterwards you want to evaluate what happened, where the sound went, or maybe you want to determine the best transducer positioning or something like that. Or you might have some kind of more complicated array system where you can do aberration correction, in which case we need to know what the pressure is so that we can do some inverse planning or the aberration correction itself, for example. So I guess this is really important because we want to be able to compare these studies. We want to know where we're targeting. We want to know how much sound we're delivering, whatever dose may be. And we kind of want to know that we're doing the same thing to each of the participants so that we can kind of get better statistics and better comparisons between studies. So what are our system components? What do we need to know about them? And then how do we put all this together to try to estimate what the pressure is in the brain during the stimulation? So I guess the systems can be sort of divided into three main parts. So we have our source, so the thing that's generating the sound. We have our participant, so we may have some medical images of them or something like that. And then we have the kind of combination of the source, the participant, and whatever other bits and pieces, whatever coupling or positioning and things like that we have to put all that together. So we kind of need to know information about these three bits and how they fit together in order to estimate the pressure. So yeah, I guess some of the challenges in doing this. So it's not obviously a straightforward thing to do. So it's something that we've been trying to work towards. And yeah, so I'm going to go over a few of the different areas that we've done some work on and some of the challenges in doing that. So first of all, some of the challenges, we need to have accurate measurements of what's coming out of our source. So we need transducer characterizations and field measurements. We need an accurate and validated numerical model so that we know when we run this source into some medium that the field that we're calculating is correct. If we want to know something about the participant, then we need to be able to convert our medical images to some kind of medium property information. We need accurate and precise registration of transducer to the participant. So we kind of need to know where you put the transducer and where the sound is going. And then we need to make sure that the sound is actually being transmitted from the source into the participant. And then, yeah, I guess when you're doing this on people, there are other human factors, how we do the registration of the thing, etc. So yeah, this applies whether you've got one element or 1,000 elements. So yeah, where do we start and what do we report? What do we tell people? So I'm going to start talking about free field pressure measurements. So this is something that I spend a lot of my time doing. So this is the bit that I know how to do well. So in order to sort of know something about our source, what do we do first? So in the simplest case, we need to know what is the source, what shape is it, how many elements does it have? So if it's a focusing source, then what's the diameter, what's the radius of curvature? Where does the focus appear? Yeah, so what's the position of the focal region and these kind of things. And then we might want to do something a bit more complicated. So as well as just saying, okay, I've measured my source, I know what's coming out of it, I know where the pressure is when this is just in water. We might want to kind of take a snapshot of how the surface of the source actually vibrates. And then we can use that information to then feed that into a model and get an accurate picture of what the source is doing in terms of the whole field. So we might end up with something like this. So this is the pattern of surface vibration on a single element focusing transducer. And then we can generate things like the axial profile, so we know where the focal region is, how long it is, we can look at how wide it is, and that kind of thing. And I guess the advantage of doing this kind of thing, where you get the actual pattern of the vibration of your particular source, is that you get some differences here in the part of the field that's close to the transducer. So I think I've got another diagram of that a little bit later. So what do we actually do? So normally we do these kind of measurements with a hydrophone in a scanning tank. So I know that more and more people are kind of getting this equipment to try and characterize the output of their sources. So just a few where you have to make some considerations of how you've set this up. So yeah, the first thing is that you have your source in the tank. You need to think about how you drive it in order to make a good measurement. So you don't want to run it continuously, for example. You probably don't want the same kind of burst that you use during a stimulation parameter, because it's going to be too long in terms of reflections bouncing around the tank. But you want it to be long enough that it's reached some kind of equilibrium state. You need to think about your hydrophone that you're using as well. So I'll talk more about this in a minute, but the size is important. The calibration that you get hold of from the manufacturer, and this kind of has an impact on, so the size of it is related to the directional response and the kind of spatial averaging effects that you get. You need to think about how you acquire your signals, so which part of your waveform you're actually recording. So for example, you might set up some burst that looks like this, and this, the bit outlined in green is the bit that you're kind of interested in. You don't want these initial transient bits or the last bits, or this kind of ring up period in this transducer here. You want some part where the whole thing has become steady, and then you can extract your numbers from this. And I would say that because in the kind of the regime of operation of these transducers, these pulses are symmetrical. They're linear pulses. The peak positive pressure is exactly the same as the peak negative pressure. So they don't have any kind of non-linearity which pushes up the peak positive pressure. So I always use the amplitude of this sine wave as the metric that I'm capturing. So yeah, then in order to calculate those numbers, what you do with the voltage signals that your hydrophone generates is important. So how do you apply your calibration? What kind of filtering do you do? And that kind of thing. And then, yeah, the equipment that you actually use to do this. So how do you position all of your things? You should make sure they're not kind of wobbling around. You want stable temperature. You want to try to minimize reflections and worry about bubbles and things like that. So these are kind of some of the things that we have to try to control. Okay, so just a bit more on how the hydrophone influences the measurement. So lots of people are kind of getting hold of hydrophones, and people are tending to buy quite large ones. You get better signal to noise ratio, but it does come with some disadvantages. So depending on the type of hydrophone that you have, the sensitivity of it can vary quite largely with frequency. So because we're interested in these kind of linear pulses, so you're looking at a single frequency sine wave, we don't need to worry too much about some of these variations of frequency because we only got one frequency in our pulse. But I guess my point is that you should make sure that you do know the sensitivity at the frequency that you're taking your measurement at, because it may be different from another point at another frequency, and if you just extrapolate or use some other frequency, it could be quite wrong. So these flat ones are membrane hydrophones, and these kind of the ones that change quite a lot with frequency are needles, and most people are using needle hydrophones. Another thing just about the uncertainty, if you get your calibration normally from the vendor of the hydrophone, they will have obtained a calibration probably from National Physical Laboratory or some other national measurement lab. And when they do a transfer calibration to your hydrophone that you bought, you basically end up with a kind of doubling of the uncertainty. So I guess if you want to reduce this, then you can pay quite a large amount of money to the National Physical Laboratory to get a reduced uncertainty. So here, kind of in the sub-megahertz range, we're talking about 9% or so, whereas the vendors might be quoting 18% or something like that. But, so, yeah, I guess where does that come from? So there are some variations because they're doing a transfer against something that's a calibration that's been transferred off another piece of equipment. There's random variations, and there's just kind of differences in what the absolute pressure level is. But what can we do about that? If we really got 9 or 18% uncertainty, do we really not know the pressure to sort of, to that precision? So it turns out that if you take a bunch of different hydrophones and then you make measurements of the same thing, the same field, then actually you do get quite good agreement. All these calibrations are obtained from the same place. So basically what we're seeing here, sorry, I've lost the pointer again. Yeah. So we made a measurement of this field, a 1.1 megahertz field, so it's a higher frequency than most of the fields that people are using here, but just as an example. And then if you compare the measurements made with these 4 different hydrophones, which are different types, membranes, needles, different sizes, actually they all come out pretty close to each other. So it's not, I think it's not terrible. And if you look at the differences between them at these kind of low pressure levels, actually we're getting within maybe sort of 3% or so. So although there is an uncertainty on that, we can have some confidence that the number that we're measuring is kind of, gives us some reasonable idea of what the pressure really is. So this here, we're kind of, if we look at this one, then this is more of an illustration of what happens when your hydrophone gets quite big compared to the thing that you're measuring. So in this case, we've got a 1.1 megahertz field. The full width half maximum here is reasonably large. So it's bigger than all of the hydrophones. They all kind of agree, even though they're different sizes. When we look at this figure at the bottom, we've got a high frequency field, which has a much narrower focal region. So what happens there is now that the hydrophones actually start to look quite large compared to this, this beam width. So they start to underestimate the pressure quite significantly. So the biggest one, this pink dotted line, sorry, that's point again. Yeah, so this one, it's a 0.4 millimeter element, and it's kind of underestimating the pressure by about 50% because it's just too big compared to the beam. And that happens because you buy the hydrophone, they tell you it's 0.2 millimeters in diameter. But actually, if you look at the effective size of this, it's actually much bigger. So it behaves like a sensor that's actually much larger than its nominal size. And that increases as you decrease the frequency. So once you get to sort of 6 or 8 megahertz, then actually it does kind of behave like the nominal size. But when you're at low frequency, it's acting like something that's much larger. So this is the collection of measurements that I made. So this 40 micron hydrophone is acting like something that's 400 microns at 1 megahertz. And then I tried to make some measurements at 500 kilohertz of the 0.2 millimeter needle hydrophone, and it seems to look like something which is about 2 millimeters wide, which is pretty big compared to your field. So I guess my message here is err on the side of caution. Don't buy the big hydrophone because you think you'll get better signal. You'd be better off with a smaller one. Okay, so a bit about source characterization for field modeling. So this is more where, rather than just looking at what comes out of our source, we're trying to work out what the source actually does. So when we've got a single element transducer, we can characterize this really well. So we can get this lovely pattern of the source vibration, and then we've shown that when you put this back into a forward propagating model, it agrees really well with with measurements. And as I said before, the part of the field really close to the transducer, there's more uncertainty and more differences there. If you assume that this source doesn't have these kind of ripples, the Lamb waves on the surface, if you assume that it's just completely uniform, the near field is a little bit different. So I guess the question then is, well, that's the bit that's passing through the skull. So then what happens? So possibly it just kind of comes out in the wash, and by the time you get to the focus, it's all fine. But I think this is a question that probably needs a bit more investigation. But this isn't quite so simple if you've got more than one element in your source. So what the next few slides are, the results are heavily dependent on the construction of the transducer, exactly how it's put together. But when you've got a transducer that's got several elements here, so there's the bowl in the middle and then there's some rings on the outside. If you drive them individually and then map the surface vibration, then you kind of see that you can see the individual elements kind of vibrating. And then if you add all of those up, you get something that looks like this. But then if you drive them all at the same time and then measure that, it looks pretty different. And the resulting axial profile is not really the same. So your focus is not in the same position and it's not the same amplitude. So then I guess, how do you then simulate every possible focal position with this transducer? You might think that you could individually take the elements and then add them up with different phases to produce different fields. But if you do that with this transducer, then you don't get the right answer. This is another transducer with more elements this time. So this is when it's all the elements are vibrating in phase. So we can't see the individual elements here. There's 64 circular elements. But we can just kind of see the whole surface vibrating. When we then steer it off axis laterally, so now the elements are kind of out phase of each other, it's easier to see the individual ones, and you can see these sort of separate blobs where the elements are. So there's something different there. Again, if we modeled this as 64 ideal circular transducers, then we're not going to get the right answer. And that's shown here, that as soon as you steer off axis, you get a drop in the focal gain because of the kind of resonances in the whole transducer. And if you compare experiment and simulation, the simulation assumes that the focal gain is kind of maintained when you steer off axis, but the experiment shows that actually you get a drop in the pressure. So if you want to take your transducer and then model, how do we do aberration correction? What phases do we need to drive it with to do this correction and the steering? You need to understand kind of exactly what's happening with this transducer, otherwise you don't actually get the right field out of it. So those previous ones were kind of more mechanical crosstalk, where there's actually physical coupling between the elements. So what happens when you decouple the elements? So you make a transducer out of separate elements. So this is made of 32 individual elements placed in a 3D printed housing. So now they're mechanically pretty well isolated, but electrically maybe not so much. That depends on the cabling and the matching networks and everything that you build. So with this transducer, we had a look at what the difference would be. First of all, if you assume that they all radiate with the same amplitude, and that all the elements are positioned where we thought we'd put them, and then you compare that to a measurement of various different fields that have been steered around to different positions, so away from the geometric focus. When you make this assumption that you have they all vibrate the same, you get the wrong answer, basically. So if you look at the red arrows at the top, we overestimate the amplitude compared to the black line, which is the measurement, and then the steer positions are pretty wrong. If we try to make some prediction of the electrical crosstalk between the different channels, which we did by steering the array to different positions, and then doing some fitting to the capacitive coupling between the cables, and then basically optimizing to fit between the prediction and the measurement. You can get the positions, the amplitudes are now correct, but the positions are still a little bit off. So then if you do holography and you back project and you can pick out exactly where all of your sources are, so in your model, we then place them exactly where the elements are in real life. And then you also predict this electrical crosstalk. Then now you get agreement between the measurement and the model. So that's shown here by these lines. So we predict the right amplitude and we predict the right position because because we understand how the elements talk to each other, when you drive one, it produces some voltage on a different one. Yeah, and these are the resulting errors. So we get about 4% error in the local pressure amplitude. Okay, so that's I guess that's the bit of the system which I feel like we can maybe understand and control the best. So what about the next part? So what's the sound actually traveling through? So if we're doing this on people, then that's our participant. So now we need to know something about if we want to accurately model the propagation of the sound and get the position and the amplitude, we need to know something about our propagation medium. So if we know what the medium is and where it is quite precisely, then we can do that quite well. So these are some experiments that were done by a PhD student in our group some years ago. So we use a bone phantom. So it's just one solid material, but it's obtained from a skull mesh. So we have an STL file of this shape, and we know exactly what the material is made of. And when we compare simulations and experiments of the field application through this phantom, we get very, very, very good agreement. So I think this is the measurement and this is the model. And then here, if we look at the comparison, even our focal waveforms, they agree really well. So this can be done if we know all of the information. But what if we don't know all the information? So if we have some uncertainty in what the sound speed is, or the density or the absorption. So these plots just show the kind of the dependence of different errors on these factors. So basically errors in any of these quantities will produce an error in the amplitude of the focal pressure. But in terms of the position, this is most dependent on the sound speed, which you can imagine, I guess, can change the lensing and the aberration and things like that. So yeah, sound speed is most prominent. And then this one is looking at sort of, what about if we think about how thick that skull is? So we've got some layer. What if we make it a bit too big or a bit too small? And then the transmission changes actually quite dramatically. So you get, because you've got sound that's propagating through a plate, and that transmission is dependent on the thickness of the plate relative to the wavelength of the sound. So if you get some error in the sound speed, oops, you're changing that kind of ratio, and then you get these kind of oscillations in the transmission, which kind of gives you some errors in the focal pressure amplitude. So yeah, what do we have to work with? How do we find out this information? So we're trying to convert, like for a person, from medical image to medium properties, and yeah, I guess there's quite a few. Obviously, everyone who's doing this kind of work has been looking at these kind of methods. So in the beginning, starting with the CT scan, and then taking possibly a scan of an electron density phantom, the same image setting as well, and then making some mapping between the density that you then extract from the CT scan to the sound speed, and possibly the attenuation. And then producing some kind of map, which you then use in your simulation. So other people have done quite extensive studies on this kind of effect, but the acquisition and reconstruction parameters of your CT can give rise to quite different images. So I guess, which one do you choose? So this one in the middle just looks really blurry, so I feel like you just wouldn't pick that one. But these two different reconstruction kernels, and then we did these with two different doses, and they, these two kind of, they don't look that different, but I think one is slightly more noisy than the other one. But then if you look at, once you've done the conversion to the sound speed and the density, then what kind of difference does it make to the properties that you get? So the blurry one obviously gives you these smoothed edges, which can have quite some impact on the transmission coefficients in the simulation, so you want to avoid that one. But otherwise, the other ones are not just, they're not too different to each other. So this is the one that we use. But yeah, I guess we try to do, or we go along to the hospital with our skulls and things like that, and we get the same protocol used every time, and we always take the electron density scan at the same time. Okay, so then what happens when we put all this together? We take our CT scan, and then we we characterized our source, and then we use K-wave to propagate this forward through the skull, and then we set up the same thing in the scanning tank with the actual skull, and we make a measurement after the sound is propagated through. How well does it agree? So the agreement varies a little bit with frequency. So we did this at different frequencies from 270 kilohertz to 1 megahertz. And you can see at 400 kilohertz and 750 kilohertz, they agree pretty well. And as other people have already shown, as you increase the frequency, you get more aberration. So at 750 kilohertz, we've got this kind of focal splitting, and it happens in the sort of in the direction where the skull is most curved, and when it's flat, then there's not much going on. So we can do reasonably well when we look at the kind of overlap of the focal regions. They do correspond to each other reasonably well, and the focal pressure waveforms as well. So we're only partway into these experiments, and there is quite some variation with the frequencies as well. So more work to be done on this, but yeah, at the moment, the pressure amplitude, the errors between the measurement and the simulation are between 5 and 30%, depending on the setup. But yeah, that was through the top of the head, where the shape is quite simple. So what happens if you put the transducer somewhere else? So these are some measurements that were done by a student of ours with the transducer positioned as it would be for a V1 study. And you can see that depending on exactly the skull and the position, this is at 270 kilohertz. So there's not too much aberration of the focus. The focus isn't split, but there are distortions, and it's moved from its intended position. And then you can see, like in this one, it's kind of a little bit curved. And the transmission loss varies quite a lot between the skulls and the positions as well. So Maria spoke yesterday, and she has a poster as well, please see her poster, about other ways of obtaining the medical image, the acoustic properties from medical images. So if you don't have CT and you only have MRI, which is obviously more likely for healthy participants, then you can get from the MR images to pseudo-CT. And she showed that the errors were reasonably small, and then if we then kind of link that back to our measurements as well, then that seems like a reasonable way of doing things. And then putting this all together, we could use something like K-plan, where you load in the participant, the CT scan, the MR scan for target selection, the CT scan for material properties, or your pseudo-CT, place the transducer and calculate the field to get out your simulated pressure, position, and amplitude. So I think I'm going to run out of time, but just a couple of very quick things at the end. So if we know something about our source and we know something about our medium, but then we need to know how to put all this together and kind of other factors which may influence in the real study, kind of what you predict, which is obviously different to taking an ex vivo skull in the lab, where you can set everything up very carefully and do it all very slowly. So what about the effect of hair on coupling? Does everyone need to shave their head? I mean, I guess for a lot of the single element studies, obviously people are not shaving their head. The transducer has been coupled onto people's hair, but it has been shown that you lose some energy, basically. So the temperature rise that you get when you've got hair compared to no hair is lower with the Insight-X systems and was. And then there's also this paper which showed that, yeah, having like sort of hair that's tied down or hair that's like waving around, apparently that's the worst configuration, just to have like free hair, so it wants to be tied down. We tried to do a bit of work on trying to work out sort of what the transmission loss is, because I guess if you're simulating the propagation of the sound, normally we're concentrating on what the skull's doing, but then you've also got a layer of hair. So we had a student try to do some experiments with a wig and basically like comb down different layers of hair. Quite a strange project. So he showed, obviously, as you might expect, that the thicker the kind of layers of hair are, then the more transmission loss you get. There didn't seem to be too much difference between measurements that he did at half a megahertz and 1 megahertz. I mean, the results were kind of up and down, but I think it's very difficult to get the hair to lie flat and then to make sure that you really excluded bubbles, and bubbles are bad news. So yeah, does everybody need to shave their head? I mean, in this configuration, you can imagine there's going to be a difference between someone with very thick hair and not much hair. but I don't really know how we take into account. And then just the last thing, positioning, which quite a few people have talked about and talked in the last session. How do we do it? What if you want to put the person back to do another session, or you've done pre-planning and then you want to put them in the place that you planned? So yeah, can we borrow? We can't really screw things into people's heads. If they're healthy participants, can we borrow from radiotherapy? This one, unless you have the mask, if you just have the bite bar, you can actually move your head quite a lot. This one does seem to be quite good, but this is what happens to your face after you've been in it. It's quite rigid and it's quite painful. So yeah, so that was a kind of overview of all the different bits of trying to do this. Probably have more questions than answers about this process at the moment. And I think this is the bit that we know well, but there's still some unknowns. So yeah, maybe we need online verification and correction of targeting. So yeah, thanks to the funders and to the bug group, and particularly these guys.
Great. Thanks for the fabulous talk. So maybe coming back to the participants' components of this. So I'd love to hear your thoughts on, so we talked about skull, but what about the stuff that's inside the skull in terms of different elastic properties of the meninges, of gray matter, of white matter, of the CSF in the middle? And I would love to hear your thoughts on how we start to incorporate that into the modeling that we're doing.
Yeah, that's a good question. I mean, I think normally we, because the skull has such a big effect on the ultrasound, that we kind of just tend to assume that the brain is homogeneous, because it's the least of our problems, I think. But yeah, I don't know. I mean, maybe, yeah, I don't know if there's some way of I mean, on the CT scan, and you don't see any sort of contrast in the brain, really, do you? It's just, it looks homogeneous in terms of the density. So maybe that's, maybe we just don't need to worry about that. So it's this, yeah, the skull that's the important thing. So I should have said that the K-wave model that we use does not include, it's not an elastic model. So it doesn't include any shear waves. It's just the fluid model. It's only compressional waves. And this has been shown to be fine if it's kind of, the sound is mostly at normal incidence, but actually we don't know how to model the kind of the microscopic structure, the trabeculae, and what happens with the sound kind of scattering. We use this sort of idea of just a, yeah, kind of average sort of porosity and change in density, which doesn't seem to give us too bad a result.
Okay, no. Thanks a lot. I love this systematic research about the impact of hair. It's one of the biggest practical challenges we have, like in the lab when applying it outside of like the temporal window. So when you get into the hair, and what I didn't catch is it the hair per se, or is it like air pockets in the hair? So is it like air being trapped in the hair that is causing issues?
I mean, I think it must be the hair itself, right? Because these, so this student that we had, this was all submerged in water, and he spent a lot of time kind of making sure it was sort of properly saturated. And I think the same here, right? This is all in underwater, and because you try to remove bubbles. I mean, I think that probably is a concern, that you have to try to make sure. So the approach that we've taken, we've done the kind of transducers coupled over the hair, is to really saturate it with gel and sort of comb it through, and then really try to squash everything together to try to force any air out. But yeah, I think it seems like it must be, at least part of it must be the hair itself. But so, I don't, yeah.
So that means even if we manage to have a lot of gel immersed in the hair and no air bubbles, it's still an issue that's a bit unpredictable.
I mean, yeah, it seems like it. I mean, yeah, I'm not an expert, and obviously the measurements that we did were not comprehensive. But yeah, it seems like there's, because I mean, if you look here and you've got, maybe when you've got a reasonable amount there, you've got 3 dB loss in pressure. It's like it's dropped to 70% of the maximum. So it's a reasonable change.
Thank you.
Hello, thank you for your talk. My question is for the people that are doing neuromodulation. There is a wide range of skulls, and some skulls are very easy to get ultrasound through and other skulls not so much. From your work with CT or MRI, do you have any thoughts on what metrics, such as the skull density ratio or something else, that could help us predict maybe like an inclusion criterion or something that we could say, oh, we saw no effect in this person because their skull is very thick? Or, yeah, thank you.
Yeah, I mean, I don't really have any suggestions other than to say that if you did have images of those people and you made the simulation and you were struggling to get a focus, or the sort of the transmission loss was so great that you really had to turn the transducer up, so you're at risk of, you know, getting skin burns or something like that, then that would be a no. But yeah, I don't think I'm the right person to ask about that. I think other people have done far more work on that.
Thanks for the very nice talk. My question is regarding the simulations to match your experimental data. So what is your take on 2D simulations versus 3D? When you actually need 3D, or can you just get away with a cross-section of the skull and that's it?
So all these were run in 3D, and I think if you just use a cross-section of the skull, then you're not getting the whole story. You know, you're not getting the spreading in the other dimensions, not getting the same kind of blending. So it might be interesting to see what you get, but it's not going to give you an accurate answer, especially if you want to do thermal simulations afterwards as well. So, yeah.
Thanks for the great talk. I was wondering if you would try maybe to quantify different sources of errors in the final estimates of intensity or focus. What would you say is the worst, what is the major sources of errors, and how do they compare to one another?
Yeah, that's a good question. But I think probably the material properties, the acoustic medium properties and their position. I think so. Maria also she looked at kind of what happens if things are shifted by a couple of millimeters, and it kind of shifts your focus around. So I think that's probably the biggest, the biggest contribution.
Let's thank Ellie again. I just want to remind everybody that Ellie is still here if you have questions and more for her. Atunka, are you going to come and announce next?
So we are going to go into the poster pitch session now. We have 26 posters and some pre-recorded pitches and some in person. So Umair will get that started. Some of them will be pre-recorded. If you see your name up there, that means it's your turn as poster presenter. So please come up here and try to stick to 2 minutes for your pitch. After the pitches, we can all go into the poster room there. We can get a drink and spend some time with the posters that are here. But please also remember to check out the virtual ones on GatherTown, which will be available, and you can potentially contact the participants through GatherTown, right? If you want to get in touch with them. So let's get started with that.
So I'll be talking about elucidating the mechanisms of transcranial ultrasound modulation of human motor cortex. Transcranial ultrasound has been shown to immediately suppress motor evoked potentials, and these immediate effects are referred to as online effects. Additionally, TUS delivered in a theta burst pattern has been shown to increase excitability for up to 30 minutes. These effects are referred to as offline effects. The current mechanisms of TUS neuromodulation do remain unclear, and so the purpose of the present study was to assess the mechanisms of TUS by administering drugs with known mechanisms together with the TUS. So 14 healthy adult subjects participated in this within-subject randomized double-blind crossover experiment. They were administered in separate sessions carbamazepine, nimodipine, lorazepam, dextromethorphan, and placebo. 1.5 hours after administration, real versus sham online TUS was compared looking at MEP, SICI, and ICF. Afterwards, we recorded baseline recordings before delivering TV TUS and then re-recorded our measures at post 5, 30, and 60 minutes after TB testing. When assessing online MEPs, SICKI, and ICF, unfortunately, there were no significant differences between sham in the translucent and real in the solid bars within any of our drug conditions, although there were trends. When looking at TB tuss effects on MEP on the left, we find that TB tuss increased MEPs up to 60 minutes after within placebo and up to 5 minutes after within lorazepam. However, we could not replicate the effects of TB tuss on SICKI or ICF. Starting with the online test, the results may have been affected by an auditory confound, which we discussed in a separate poster, making it difficult to observe interactions of tested drugs. Offline TB tuss effects on MEP were reduced/eliminated by all interventions compared to placebo. This suggests that TB tuss induces plasticity mediated by the NMDA receptor. It's blocked by activity of the GABA A receptor, and it involves voltage-gated sodium and calcium channels in the human M1. Thank you. I'll be talking about elucidating the mechanisms of transcranial.
Hello, everyone. My name is Tom Augier. I'm a first year PhD student at LATO in Lyon. And my poster entitled Achieving Controllable In Vitro Focused Ultrasound Neurostimulation for Investigation of the Underlying Mechanisms. I'm going over the first results of a study performed at LATO, which is part of a bigger project where we aim at gaining insights on the mechanisms underlying neurostimulation and ultrasound neurostimulation and modulation. And so in this specific study, we took a quite simple neural model consisting of a two-dimensional human neuron cell culture. We went back. Okay. Oops. We went back to the fundamental building block of ultrasound neurostimulation procedures, which is the single pulse. And we used calcium fluorescence imaging. Okay, yeah, to try to assess the activity of a large portion of the network. And we aimed at finding a set of ultrasound stimulation parameters to evoke causal neural activity and in a controllable and repeatable way. And so with those results, we looked at the spatial control dynamics of the response we observed. And we actually compared those dynamics with existing descriptions of the effects of mechanical perturbations on cells and try to draw links with descriptions already done in the literature. And so if you want to know more, come and visit me and look at my poster, which is this one. Thanks.
Hello, my name is Salvador Guinjon. I'm a clinical psychiatrist, and this poster reflects very briefly our first attempt at neuromodulation using a recently acquired focused ultrasound device, the NeuroFuzz. In our institute, I work at the Laureate Institute for Brain Research and on University of Oklahoma, Tulsa, Oklahoma. And basically, we have an obvious interest in clinical applications of neuromodulation. So in our first use of this device, we went right to target the anterior limb of the internal capsule, specifically in its ventral portion, because it is a very well-established target used for depression treatment, especially treatment-resistant depression, and is known when it is efficacious to change the autonomic balance towards either increased vagal parasympathetic activity or decreased sympathetic activity, or both. Depression is characterized by increased sympathovagal balance, and this intervention is known to revert that. So we wanted to test in two stimulation conditions based upon a recent paper by the group of Robert Chan in Toronto. We use a stimulation intensity somewhat lower, another somewhat higher than what is reported to be efficacious and safe. And we observed that we did online heart rate variability analysis about 5 minutes before, during sonication, which lasted 80 seconds, and 5 minutes after. And what we saw is that during sonication, there is, of course, it's very difficult to see in the screen, but during sonication, we believed to have observed, I should say, because this is n equal 1, a reversal of the sympathovagal balance towards more vagal activity, and which not lasted with the less intensity stimulation pattern, seemed to last for about 80 seconds in the second stimulation pattern. And then in 5-minute epochs, we did not really see a sustained change in this sympathovagal balance. Again, the limitations are so many that it would not be enough 2 minutes to mention them all. But if this is replicated in like in a decent sample of participants, we hope we might be able to use focused ultrasound to target not only gray matter, but also white matter tracts, which is important to test brain circuit symptom relationships. Thank you.
Hi, I'm going to talk about the effects of masking conditions on auditory compound of transcranial ultrasound of the human motor cortex. So transcranial ultrasound, or TUS, is a promising technology which has been shown to suppress motor evoked potentials. However, recent efforts in our lab to replicate previous results have found small effects when using a novel masking condition. So the purpose of the present study was to assess the effects of two masking conditions, FUN22 and Braun et al. 2020, and 2 sound durations, so only during the TUS versus enveloping the TUS on TUS effects. So 10 healthy adult subjects were recruited. FUN22 and al.'s method was a 12 kilohertz sine wave delivered through speakers on the left side of the subject's head. The TUS was delivered, and Braun and al. used a 1 kilohertz square wave delivered through earbuds in both ears. Mask delivered during the TUS is referred to as short duration, whereas masks which start before and end after TUS are the long duration. We first looked at the effects of the sound mask on MEPs alone. First, we have our no sound baseline. You find that only the 12 kilohertz sine wave short duration was able to significantly reduce MEP amplitude here on the y-axis. And so this is actually the same sound mask used by FUN22 and al. 2020. When looking at the effects of the sound mask on online tests, the translucent bars are the sham and the solid are the real. You find that although none of them are significantly different from one another, there are differences in the trend. So long duration sounds actually have a higher real TUS condition, whereas short duration sounds have a higher sham TUS condition. The sound mask delivered by FUN22 and al., as I showed, was able to suppress MEPs, and it's interesting to note that it was designed to mimic the TUS sound. There were no significant effects of TUS, but more subjects have been collected to analyze data. However, it appears that duration of sound mask may affect the trends of real versus sham TUS. So further data and studies are warranted to assess the interaction of TUS, auditory confounding, and the qualitative features of sound mask utilized. I'm going to talk about
Hi all. I will be presenting a poster named Transcranial Ultrasonic Stimulation of the Human Amygdala During Threat Learning, where we use TUS, which can provide us with causal evidence through neuromodulation of certain, especially deep brain structures that we're interested in. We combine this with a well-established threat conditioning paradigm, or fear conditioning as some people might know it, in which humans or animals learn to associate, for example, visual cue with an aversive stimulus such as a shock. It's nice because it has quite robust physiological markers. And with neuromodulation approaches, we know there's quite some variation in effect, so we need really robust outcome measures. And from animal studies where they lesioned animal amygdala, or from human patient studies with specific lesions to the amygdala, we know that there seems to be some causal involvement of the amygdala in these both processes. So we set out with this question: is there a causal role of the human amygdala in threat learning? We used, as I just mentioned, a threat learning paradigm in which snake images were either paired with a shock or never paired with a shock. And we made blocks in which we had two pairs of these snake stimulus, and one block was always paired with Verum TUS plus an auditory mask, which, as you've learned, is quite important, or can be quite important. And for a sham TUS block, where we use the 1% duty cycle, where there's basically almost no energy that goes into the brain, but you can hear the device turn on and off, and also an auditory mask. This is what the setup looks like. And we use neuronavigation to track the location of the transducers. So technical pilot results. So we administered TUS during acquisition, so during the period in which people learned about the association, and the dotted lines represent the Verum condition, and the green and the red line represent either the shock stimulus CS plus or the never shock stimulus CS minus. And you can see that in the skin conductive response, which is an estimate for arousal levels, that in a sham condition, people nicely differentiate their physiological responses to shocked and non-shock stimuli. But in our technical pilot, we didn't see the differential response when we applied Verum TUS. Then afterwards, we did a short distractor task, basically a washout period to make sure that there were no effects left in the system. And we did a short cued recall in which we again showed the snake stimuli, but this time always paired with sham TUS and with the auditory mask, so people still felt like they were being stimulated. We asked afterwards, seemed to work quite well. We did a short reinstatement, so they felt the shocks again, and then we again checked their responses to see whether they're not just online effects, but maybe also plasticity-related effects on learning that might outlast our online stimulation. So we're gonna look at targeting accuracy with simulations, and we're also gonna run a group both for amygdala and for hippocampal stimulation to look at specificity of effects. Thank you. See you maybe at the postdoc.
Hello, everyone. My name is Dong Liu. I come from Columbia University. As you may know, recent studies have been used to writing state function MI to evaluate modulating effect of FUS neuromodulation. However, no prior study has been looked at the effect of FUS modulated BB opening on primates. For this study, we aim to measure and compare resting state functional conductivity by applying FUS exposure and BB opening in the dorsal stratum of monkeys. There are 6 monkeys involved in this study. 2 monkeys were chosen for FUS combined with microbubble. 2 monkeys were chosen for FUS exposure only. For all these 6 monkeys, we collected resting state function MI as a baseline control. For groups involved with FUS, we collected resting state function MI 45 minutes after FUS sonication. We use a method called state-based correlation to codify the effect. There are 2 states chosen in this study. The first state is dry-carded, which is also the target of FUS exposure. Second state is 46D, which belongs to dorsolateral prefrontal cortex, and it is also an important node in default model network. What we found is that both FUS and FUS with microbubble can activate the functional connectivity between caudate and multiple cortical regions, and also nodes within default model network. We also found stronger functional connectivity when applying FUS with microbubble. However, difference between FUS exposure and FUS with microbubble was not significant, statistically significant. Thank you for your attention. My name is John.
Hi, everyone. I am Soha Prabhu from the Donders Institute, and my poster is going to be about transcranial ultrasonic stimulation of the human frontal eye fields. So with a relatively new brain stimulation technique in humans, it's really important that we carefully study the effects of ultrasound in humans. And I think a problem that many of us encounter right now is what protocols to use when you design your study. So we try to tackle that problem by trying to translate existing well-established animal protocols to humans. And for this purpose, we're using a 50% duty cycle, 500 hertz pulse repetition frequency protocol, an online protocol, I should say, that has been used by Kubanek and colleagues. And to study its effects, we are aiming to simulate the frontal eye fields of the humans in a choice-making test. So here, the participants are asked to make saccades to either the left or the right target that appears on the screen. While they receive stimulation of their left frontal eye field, the right frontal eye field, or no stimulation at all. Something I forgot to mention, the frontal eye fields are really important for making eye saccades to the contralateral side. In all conditions, they received also an auditory mask, as Sjoerd just said. I think we've learned that it's really important to add it. We used a block design in which every stimulation intervention block was always followed by a sham block. So based on a previous study, we expected to find online and excitatory toss effects. So that means that we expected to find more rightward choices when we stimulate the left frontal eye field and more leftward choices while stimulating the right frontal eye field. And obviously no changes in the sham blocks at all. What we found was something slightly different. So I should say this is only a technical pilot with 3 participants. And even though it's not what we expected, it's still very interesting because it taught us a lot on how to further design our study. So while keeping the same protocol, we are changing now the saccade test conditions and design. And if you're interested in learning why and how we're doing it, please stop by, and please do stop by because I'm really curious to hear your thoughts as well. Thank you.
Hi, my name is Sarah Terry. I'm a PhD student at Fraunhofer IBMT in Germany, and I'd like to talk about 3D passive acoustic mapping and especially about the impact of matrix area, aperture size, and element count. So what is the motivation of our work? As you all know, ultrasound therapy has emerged as a valid treatment option for multiple clinical scenarios in the recent years. And this comes in hand with a growing need for precise, fast, and reliable monitoring. And MR-based monitoring is still the clinical standard, but ultrasound-based methods gain in importance as they are able to overcome several limitations of MRI. And one of these ultrasound-based methods is the so-called passive acoustic mapping. And this works for monitoring cavitation bubbles during treatment. And despite the potential of a 3D monitoring in terms of safety, most implementations remain in the 2D regime, for example, due to hardware requirements. And in our study, we wanted to investigate the impact of matrix area, aperture size, and element count on the reconstruction quality. And to do that, we first simulated different aperture sizes while the element count stayed the same. And in a second step, we changed the element count based on the same aperture size. And in addition to the numerical part, we also were able to acquire cavitation signals experimentally with 2 different matrix arrays that have different aperture sizes. So the aim was to find optimal configurations while minimizing the number of needed electronic channels. And what we could see in both the numerical and the experimental part was that the aperture size has a high impact on the point spread function size. And on the other hand, reducing the number of elements results in a low change of the point spread function only. So you can say that 64 elements on a large aperture are sufficient to localize cavitation bubbles within the range of a few millimeters. And this leads to the suggestion that a large aperture is crucial to create high resolution, while the element count plays a subordinate role only. And future work is going to be the evaluation of non-gridded array geometries and also the adoption for transcranial therapy applications, of course. So I hope I made you curious, and I'm happy to meet you at my poster.
Hi everyone, I'm Umair Hassan. I'm a PhD student in Till Ole Bergman's lab in Mainz. And I will be talking about the recent developments in our robot navigated transcranial ultrasound stimulation in humans project. So we all appreciate the exceptionally well spatial resolution of transcranial ultrasound stimulation. But the way we are nowadays applying in most of the labs in humans are like these, and like manually with hands or with some straps and some 3D printed holders. And we really compromise the spatial resolution of the transcranial ultrasound there while we are applying it. So we took on the project to basically repurpose the TMS cobot, or the transcranial magnetic stimulation robot. And basically, we had several design criteria in our mind that the robot with the transcranial ultrasound stimulation capabilities should have the sub-millimeter accuracy of transducer positioning, and should automatically rectify or compensate the head motions, and it should be able to go to multiple regions within one session without any problems. It shouldn't apply a lot of pressure to the coupling media, And then we have a variety of sizes and shapes and weights of the transcranial ultrasound transducer, so it should be able to hold all of them. And last but not the least, that there should be no head fixation required, or minimum head fixation should be required. So basically, we then built some metallic adapters and some 3D printed adapters, and then took up the local light neural navigator and make it compatible with local light neural navigator. And here you see on the screen the 500 kilohertz transducer hooked up with the normal cobot, but there is no TMS coil in this case. And this is the design of the adapters. Like, it's a universal adapter. It can hold at the moment 2 adapters, but the idea is that it can be able to adapt hold multiple transducers. And here you see the results in a neural navigated environment with a human head. And yeah, so I would like to thank my team in TILS Lab, and specifically the Axulum Robotics team and Localite team to make it possible with us. And let's connect in my poster. Thank you.
Wasn't there a mouse or with the point? Okay, yeah. Yeah, well, I guess this works as well. Well, obviously it's my first time here, so thanks for the opportunity here. Yeah, and thank you for your interest in my poster with the title Inhibition of Conflict-Related Midfrontal Theta with Low-Intensity Transcranial Focused Ultrasound targeting the right prefrontal cortex predicts greater approach versus withdrawal behavior in a virtual team-based human subject study. So this already gives you our conclusion, and I will show you real quick some key aspects, how we got there. So bear with me for 1 more minute. For introduction, we built on earlier studies using LitFuzz targeting the right prefrontal cortex, in short RPFC, which has been shown to enhance positive as well as decrease negative subjective mood and inhibit fMRI midfrontal affect regulation network activity. Details can be seen right here below, also something I would like to discuss at the poster. In our pre-registered study, we wanted to explore EEG and behavior as further objective measures in a virtual team-based task paradigm. And based on the aforementioned work and details shown here below, we hypothesized, as written here in purple, that RPFC LitFuzz should inhibit conflict-related midfrontal theta, and this inhibition should predict heightened approach and lower withdrawal. Details on a paradigm, again, here depicted on the right, and something I would like to discuss at the poster. In short, to the results, as you can see, we collected a relatively large sample size since the time frame for hypothesized effects was between around 50 to 100 minutes post-LitFuzz after relatively long EEG and paradigm setup time, so effects could be potentially small. What you can see is that LitFuzz led to a significant inhibition of midfrontal theta as measured at electrode FCZ for all the events of our teammates paradigm. This is the gray circle on the right. And we observed the typical midfrontal theta burst pattern with the inhibition distinctly visible in the difference plot at FCZ, see on here on the left below, and in the difference plot here on the right. And most importantly, we see distinct prediction patterns as hypothesized, most clearly for our so-called ambiguous events, where we had the highest conflict potential. And we see a negative blue prediction spot here for withdrawal out of the teammates, and a red positive prediction spot for approach into the teammates. So this matches our pre-registered hypotheses. Again, more details, and yeah, with that, I hope to see you at the poster over there, and thanks for listening.
Thank you for coming to my presentation. This poster is titled Transcranial Ultrasound Neuromodulation Induces Neuronal Correlation Change in the Rat Somatosensory Cortex. Ultrasound is an exciting neuromodulatory technique in which you target the brain with a low intensity acoustic wave. It has high spatial focality and the ability to target deep brain structures and has been observed to induce a lot of neural responses. But for future clinical translation, we're specifically interested in whether it can induce sustained changes in network dynamics and in excitability, which is what we attempt to test here. Specifically, we try to stimulate the anesthetized rat brain using different frequencies to encode for different types of plasticity changes. We target the brain at the somatosensory cortex opposite to the recording electrode with ultrasound. Here, as you can see, so that the recorded from area has peak ultrasound intensity. We deliver electrical stimulation at the hind paw in trials every 5 seconds, then deliver ultrasound for a 5-minute period, and then go back to the electrical stimulation trials to observe the difference. And here on the left, you can see the ultrasound waveform delivered. What we observed is that there was an increase in excitability following ultrasound in the recorded neurons compared to sham. We also observed that there was significant modulation of correlation compared to sham after ultrasound. And here we observed that there was a dependence on frequency, where mostly we observed increases at high frequencies and decreases at low frequencies. You can see this in the group analysis, where here we see mostly increases in the ultrasound compared to sham and control. And you see the same effect in correlation, where again, we're seeing changes in both directions, but on average, we see changes as well. Here you can see the way that there are different amounts of increases versus decreases. We've broken it down to show that the high frequencies show more increases, while the low frequencies show more decreases. We also observed that there was a difference in the correlation effects induced between cortical layers, implying that there may be some amount of cell type selectivity related to the morphology differences between the different cortical layers. So yeah, in conclusion, we found that ultrasound within our waveform paradigm could modulate excitability and correlation change in the recorded from area. Thank you for listening, and these are my references and acknowledgements.
Hello. In this study, we used a ramped ultrasound paradigm to look at the effects of ultrasound on the primary visual cortex. And we did 2 different experiments within this. The first one that you see above is we applied 300 milliseconds of ultrasound every 2 seconds. And this was in order to look at an effect which has been shown previously with unramped ultrasound, where only applying ultrasound to the visual cortex evoked a potential in the EEG, which looked a lot like a visual evoked potential. What has also been shown in the literature, and this is in the somatosensory cortex, is that if you have a potential that is evoked by a sensory stimulus, so a median nerve stimulation, when you apply ultrasound time locked to that median nerve stimulation, you get some modulation of the sensory evoked potential. So in order to test for that, in the second part of this experiment, we had those vertical lines depicting screen flips, a checkerboard change in the colors, which robustly elicits a visual evoked potential. Some of those trials were associated with ultrasound, which was either a real or a sham condition. In the sham condition, the device was turned on, but the power was set to 0. And what we found very briefly is that we were not able to see the evoked potential that has been previously shown without any visual stimulus. So this is just ultrasound being applied. And we also don't see any difference between the real and the sham conditions. When we do have the visual stimulus, one thing that we see is that in all 3 conditions, real, sham, or no ultrasound, there is a visual evoked potential that is visible in a number of our EEG channels. When we compare the real stimulation to the no stimulation condition, we see that there are some differences that are picked up by a cluster-based permutation test, which seem to occur at approximately the -75 millisecond peak, which is believed to reflect the afferent volley arriving in the V1. We, however, do not see any difference between real and sham, and therefore we think these are preliminary. Maybe we were underpowered for that because we didn't have quite as many real and sham trials. If you would like to know more, please come to my poster.
Hi, everyone. I'm Maria, and this poster is about the same work that I talked about yesterday, but I will reiterate as a reminder or for anyone joining today. So basically, we're exploring how to generate pseudo-CT images from MRI images. And we're doing that to avoid exposing people to ionizing radiation through the CT scanner and also getting an accurate image of their skull so we can use it in TUS studies. So we explored two different kinds of methods, a classical one from ZT images to CTs, which the gist of it is basically a linear mapping from ZT to CT Hounsfield units. The second, more complicated way is we implemented a 5-level deep convolutional neural network, specifically the UNet, and that learns the mapping from MRI images to CTs. We did that with two different kinds of images with a ZT and a T1. We also evaluated the results two different ways. The first one is a typical voxel-based method. So just comparing voxel per voxel, the pseudo-CT to the CT. And the second way is with acoustic simulations, because since our application is TUS, we care about getting the acoustic properties right. In all three cases, the ZT results do seem to be better from the deep learning method, and it gets more accurate Hounsfield unit values. It gets the acoustic pressure correct, the position, and the focal volume. If you need to, if you have any questions, feel free to talk to me at the poster. Thank you.
Today, I will be presenting our work showing that transcranial ultrasound stimulates neurons at the focus in mice. The motivation for this work was to address the lack of response at the focus in prior GCAM imaging studies. The cortex-wide response from Sato on the right called into question whether ultrasound can have a localized effect on neurons. We redid these experiments with different pulse schemes, among other differences, to demonstrate that ultrasound can have a direct stimulatory effect. We used wide-field fluorescence microscopy to assess neural activity in response to ultrasound in transgenic male mice with surgically thin skulls. In these images taken with our system, we see strong activation at the focus, marked in the first image, at a latency of about 1 second after the start of sonication. We observed that the focus shifted with transducer placement between mice and thus registered our images by their peak fluorescence for part of our analysis. Given the pressure profile produced by our ring transducer, we also analyzed the fluorescence in concentric 1 millimeter thick rings moving away from the focus. Some of our key results show a localized response to smooth waves, which we've previously shown to mitigate the auditory confound. Recapitulating this effect, we see much lower fluorescence in the ipsilateral auditory cortex than at the focus with a smooth wave, and at a longer rise latency. As a control, we also analyzed the fluorescence in the visual cortex, showing even lower activity and longer latency, indicating likely activity propagation. Finally, we show that the response at the focus increases predictably with both increasing pressure and duration, and decreases as you move farther away from the focus. We also see a somewhat linear trend of the response to pressure times duration, and a very strong fit to pressure for a particular duration, indicating a larger dependence on pressure than duration. I look forward to answering any questions at poster 1021. Dan, will you present?
Hi, I'm Tony Phipps. I'm a postdoc in Charles Caskey's lab, and my poster is about kind of retrospective analysis of our optical tracking and localization in ongoing neuromodulation experiments. And so this is actually some of the data from Lamin Chen's talk from yesterday. So to start with, what do we want to do is, as you've probably seen, a lot of people are using optical tracking in order to try and target specific areas of the brain. However, there can be issues with this. Optical tracking tends to have 2 to 3 millimeters of error due to just errors across the transforms. And as I'm sure you're convinced by, this skull can also cause focal shifts in the beam. So what we wanted to do was do optical tracking of a phased array transducer that would allow us to do electronic beam steering so we can then correct for these errors after an initial sonication. So an example of how this looks in kind of the real world use is shown on the right here, where we have the green cylinder is the projected estimated focal location. And the top right, you can see all the individual elements of this transducer. And when we do this in practice, we're able to then see where the estimated focus location is as this green cylinder. We perform MR-RFI in this color map overlay. We can see, and then we have a target that you can see off to the left side of this image. You can see we didn't do a great job of putting the transducer on the target this day. We had a little bit of lateral error, which you can see from the RFI not being aligned with that green circle. And we're able to then use that information to correct the beam and hit the target, which you can see in kind of the center image. Then on the right of this is kind of a summary of our data. So across these studies, we saw approximately 5 millimeters of error with our optical tracking system. And then when we look at our new steered coordinate compared to the target of interest, we reduce that to about 1.4 millimeters of error. So I think kind of my main conclusion is optical tracking is great, but if you have a sufficiently small target and sufficiently small focus, you need to really think about, are you hitting your target of interest and what other tissues might you be sonicating, and then see if you have a way to try and correct for this. So that's what I could fit in 2 minutes, but please come by my poster if you'd like to hear more.
Okay. Just making sure this works. Yep. Okay, so you have really already had much more than a pitch about this work with Citi's presentation this morning and Elsa's presentation yesterday. So sadly, I can't really tease any of the results because you've basically seen them already. But I'm sure your interest was already piqued with the previous presentations. And if you come to our poster, I'll try to answer some of the questions and the discussion points that were mentioned during the presentations. So just to recap, we stimulated the dorsal anterior cingulate cortex and the posterior cingulate cortex in 24 healthy human participants using the protocol described by Zheng and colleagues as having excitatory neuromodulatory effects in humans. And so we measured GABA concentrations in both regions of interest using MR spectroscopy, as well as recorded made 2 acquisitions of functional activity at 15 and 45 minutes post-sonication. And what we found is that TUS significantly decreased GABA concentrations in the PCC after sonication, and sonication also increased functional connectivity of the PCC with a set of particular brain regions, as you can see here. Now, as mentioned by Citi and Elsa, the DACC did not seem to show any response to sonication. And actually, we're kind of counting on your guys' input and any clues you might have as to why the effects were not seen in the DACC. So we'll be discussing the potential state dependency of TUS. This is the default mode network. So the PCC is one of the main, or the main hub of the default mode network at rest. The importance of focal volume, but also tissue composition and potentially differentiated channel expression throughout different regions of the brain. And and also different functional and structural connectivity profiles for both regions. And potentially that could be driven, for example, by the presence or absence of the paracingulate sulcus that you can see here in the posterior PCC, anterior CC, sorry. So yeah, as you can see, there are many questions consistent with a lot of the talks here, many questions to be answered. So yeah, please come to the poster so we can try and get some of the answers.
Okay, sorry. Hi, everyone. So I also gave a talk yesterday, but just in case anybody missed it, we're going to do a really fast recap. So our work focuses on the auditory confound, and here I'm just going to briefly run through it. So we apply TMS over the primary motor cortex, and what we get there is an MEP that we measure with EMG, and the amplitude of that MEP is thought to reflect motor excitability. So when we apply ultrasound at the same time, we expect to see a change in that MEP amplitude that would reflect a TUS-driven change in motor excitability. Now, that approach has been taken before by a number of researchers, including Dr. Flamenco, Dr. Shia, and Professor Lagon, and they've all observed online motor inhibition. Flamenco also really highlighted the substantial impact of stimulation parameters here, particularly stimulus duration I'm highlighting, where longer durations more significantly attenuate MEP amplitude. So let's move to our own work. In a first experiment with 14 subjects, we looked at a number of conditions, including a control condition in which we stimulated a control region, and also a sham condition where we just administered a sound alone. We also did those both with and without a masking stimulus to block any potentially audible differences. Here are exact stimulation parameters, and as you guys know, we also followed that up with a second pre-registered sample of 32 participants, also with some technical improvements. So if you want to talk technique, please come to my poster. I'd also like to highlight here, since we had a question yesterday about any potential drift and excitability throughout the experiment, the role of perhaps repeating TMS at a low frequency throughout the experiment. So just to explain a little bit more about our baseline conditions, in the first sample, we used a blocked design. And there was a baseline block within the first 4 blocks and within the last 4 blocks to try to capture drift and excitability. In the second study, we moved on to an interleave design, and we had baseline trials interspersed throughout the entire experiment to capture any drift and excitability. So I hope that helps. Really running over the results super fast, we have online motor cortical inhibition, and again, very sadly, that's not specific to ultrasound. So we see that stimulation of a control region and sound alone also cause this reduction. When we look at stimulus duration, shorter durations don't significantly affect MEP amplitude, while longer durations do, but that same pattern is observed for both of our control conditions as well. We don't observe any extra relationship with stimulus intensity in spatial peak pulse average intensity, nor do we see a clear pattern in individualized simulations of actualized intensity at the focus. And in our repeat experiment with 32 participants, sadly, we are again seeing this relatively flat line, regardless of stimulation intensity and also regardless of masking stimuli. I encourage you to come to my poster if you have any questions. I'd love to talk with you guys, and a lot of you have thoughts that I would love to hear about as well. So please come by, and thank you to my lab. And I want to give a special thanks again to Judith Lefkes, Stuart Meyer, Soa Farwood, and Marwan Engels for helping with this project, and Brittany van Beek, and of course, Jennifer Hacker, who is my boss. Thank you.
My poster is on simulations of ultrasound focused to the C5, C6 region of the cervical spine. And we're doing that because we're interested in potentially doing ultrasound neuromodulation in the spine as opposed to the brain. There might be potential experimental or therapeutic applications to that. It's not been done to my knowledge. So before we proceed to any sort of experimentation, we need to make sure that this technique is potentially safe. And one way to ensure safety is via simulation. So I built a simulation system using CT data of a whole body, and then applied spinal sound speed and skull acoustic data because there's no spinal attenuation data for the spine. And then worst case scenario thermal properties for the spine. And then next, used K-plane to position an array with, I guess, a bunch of acoustic property, sonication parameters that will be on my poster to focus ultrasound to the spinal cord. and record the evolution of pressure and temperature distributions. And you'll be able to see the interesting pressure profiles on my poster. Talk about this more later, but the pressures were limited to under 0.6 for a mechanical index. The transmission efficiency was anywhere between 20% and 50%, depending on the target location. The heating was mostly restricted to the bone. It didn't diffuse too much into the spinal cord. The heating in the bone was between 1 and 2 degrees at the spinal cord with the sonication parameters I used. The heating artifact, the heating neuromodulatory artifact shouldn't be a problem. So this is just the first step towards showing that this technique could potentially be safe. The spine is a complex bony structure, much like the skull, and there's been less work done on it. But hopefully it's a promising first step towards ultrasonic neuromodulation in the spine. Thank you.
So hello everyone, I'm Elena Viteri, I'm a PhD student in EPFL in Switzerland, and I work on stimulation of peripheral nerves. So while ultrasound for peripheral nerves, there are a lot of patients that suffer from peripheral nerves and spinal cord injuries, and therefore they have impaired sensory motor functions, and so ultrasound would be like a great solution for them for the reactivation of motor circuits and also for the restoration of the sensory feedback. Also, like in particular, ultrasound, studying the recruitment properties, fiber-specific recruitment properties, we could get multimodal sensory feedback. This means, for example, having different kind of feedback, such as touch, temperature, proprioception together. So therefore, we designed this ex vivo experimental design based on a nerve on a chip platform that you can see in figure, that is based on microchannel electrodes. With this platform, we can stimulate electrically, stimulate with ultrasound, and also recording the compound action potential that is propagating along the fascicle that we put inside. The objective of our study are to characterize the fast evocative responses in these peripheral neural fascicles, so exploring the stimulation parameter space, but also disentangle the recruitment properties of ultrasound regarding the different fiber types. So now there is not so much time to talk about the results, but I would really like to discuss them with you during the poster session after. So thank you very much.
Thank you. Please get a drink from right there and join us in the poster hall. At 5, Brainbox will be doing a workshop here, so please do come by for that also.
I actually, slowly fired. What about you? Yeah, getting there. Yeah, but you still have to, what's the thinking about? So Kyle is going to, do a bit of a question and answer, moderate about Neurofus in general, and then we'll show some key plans. A bit of an overview. Okay, thanks. And when you get some time, maybe this evening or tomorrow, maybe we should have a chat about the system and when we want to see you and like we said about email. Yeah. Plan that. Yes. Plan that. Yes. Or we can follow up after by email. I think no, and that's more the project because also our his people could be involved in that. Yeah. We yesterday mentioned the one that after okay. Because there's some people away and blah, blah, blah. Yeah. Would that fit? Yeah. I was thinking end of October at the earliest, but after SFN would also be cool. Yeah, maybe we'll start earlier. If there's a question to you, but yeah. Because if it would be helpful to do a quick online connection to get started, we can also do that and fit that in at any time, really. Yeah. And then it sounds like a mixture. Okay, so let's try this mixture. Yeah. So then that's good. Yeah. Okay. I'll follow because there's especially
two people in our lab who will start doing this practical part. Yeah, and one is actually here, that's Mikko. Yeah, and I think it would be good that those get the urgent, yes, online, a bit of hands-on time, yes, exactly. And then there'll be more useful questions, and then later on, yeah, and then we can also have a little bit larger group then there. That would be perfect. Okay. There you go. Yeah, no, I'll follow up with you on that then. Yeah, yes. Also on the EULA, I have now kind of the answer. I think it should be okay. But obviously we need to make that call. But yeah, I think that's going to be easy to go because you listed the points, and I think it would be easy. Yeah. So okay, so perfect. Yeah, I also I don't want to think that anything will happen. Like basically that it will respect software from all the systems, and it will be a little bit. Yeah, they shooting ourselves in the foot. And in reality, we've got no means to do it. We've got the systems are not connected to network. We can't press a kill switch several, and so we simply can't force an update on it without you agreeing to actually. So those kind of things. Then doesn't make it. Why is it in there? I'm completely with you. Okay, yeah. But at the moment, that's the version we have available, and that's what we need. But our lawyers like I'm not surprised. I think other institutions. I think maybe you should do the job and. Good.
So this. That's. Yeah.
Oh, I don't have it. Oh, no, I mean, I'll just talk. Okay. Oh. Actually, I did send. Yeah.
So that works in Hi.
K-plan. I do with a K-plan.
Good work, Steve. Good. Well, there's some online people that want to see it, so I'm gonna carry on for the online people and Sam. So yeah, thank you, virtual audience. We'll get started. So for those of you that don't know much about K-plan, it's basically K-Wave but with a graphical user interface. Feel free to shout if you can't see anything or can't hear anything. I'll try and keep an eye on the chat. I've got no idea how. That was an answer to a question in the audience to turn up the volume here, but it's okay. I'll carry on to the online audience. So, yeah, K-Wave, really powerful tool used in a lot of research already, MATLAB driven. But if you're not a physics engineering expert, it can be a little bit tricky to use. So with K-plan, we've made that user interface a lot easier, hopefully. I'll just show you a quick example of an end result, some modeling we've already done as an example, just to see what the end result is like. And then I'll go back to the start and show you how we got there. I just need to get that back. So this is an example of a free field versus skull. Bear with me. Focus on the center. So positioning the transducer in free field versus what it's like going through the skull. The position of the transducer here is obviously where it was for the skull, and then the transducer is quite clearly over here in the free field. We can move that around and see how it's affected. I have a few different examples for you to see what it's like, different angles, different incidences, going through different types of bone in the skull. But this is what we're trying to get to at the end. And we can read out other properties as well then about the sonication parameters, exactly where, if I go over here, exactly where the transducer is positioned, XYZ coordinates, vectors, and that can be translated across to neuronavigation systems, so you can be precisely in the correct location. Or vice versa, you can take those coordinates from neuronavigation and validate what you delivered or what you thought you delivered based on the individual subjects. So I'll now go back to the start, and then I'll come back if there's time to look at some of the other examples that we have in here, changing the focal distance, using a NeuroFuzz system, different frequency transducers, the incidence angle. That's always a nice one to see. Right, so add new. One thing I've done already with this project is set up the images for this subject. So we need ideally a CT scan as well as an MRI scan, so you can see the brain structure. You can work with pseudo CT or zero time echo. You can just select which one is your primary planning image. Obviously CT being the gold standard right now, but you can kind of work backwards from there if it's not available. There is also a template MNI, CT, MRI built into the software, which you might think defeats the object of this kind of accuracy and this kind of modeling, but it can be helpful for at least getting some example data for grant applications, or just proof of principle if you don't have access to real subject data. So once we've loaded the images, then we can pick a live example. Actually, the images are in the next step. Sorry, I'm getting ahead of myself, but I need to select the transducer first. Now, again, these are just some example transducers, but if we have the details of the system that you're using, based on calibration data, based on what the manufacturer provides you, obviously, we at BrainBox work with NeuroFus, so we have all the NeuroFus transducers, or most of the NeuroFus transducers included. And if you have a NeuroFus system, we have a specific calibration file for you for that a particular serial number based on the calibration data that we get from Sonic for that. So these are just some examples. We're starting to add BrainSonic's transducer to this as well, together with Noah and his team at Brown University. So those would be available to select or add new ones if you do grow your lab's capabilities as you go forward. So once I've done that, now I can load my images, and I'll just do the easy version, add the MNI templates, and you can see it adds the CT and the MRI automatically. But if I did want to add my own new image, and CT example, this is where I can tell the system what type of image that is. Those are all the various options that can be added, and inform the system that this is the primary planning image as well. So I won't do that because I'm using the template. Next, into the planning step, again, I can change all of these different views so you can see different things, look for the structure that you're interested in. First step is going to be to select or set my transducer location. I'm just going to do that arbitrarily. It can be done much more accurately by importing files, as I mentioned, from NeuroNavigation, so you have the precise coordinates. Or if you're trying to find out where best to place the transducer, given a certain structure, that's what we can do through this iterative process of improving the simulations each time we try different locations of transducer. So with the appropriate tool selected on the left-hand side, I can select the origin of my transducer, and then with the arrow, select the direction for that, normally towards the direction of the brain structure you're aiming to target. That's not necessarily to say that that's the finished orientation you will end up with, that will give you the best results. And you don't need to worry about distance at this stage. It's just to give you a vector that we can then place the transducer on top. So it knows, obviously, the transducer I've selected, knows the properties in terms of dimensions. Let's see. That's the wrong one. Shift. Knows physical dimensions, but more importantly, it knows the elements, the focal depth, the range that it has available. If I now want to adjust that, maybe based on different views, for example, in the coronal view, I want to adjust it maybe left or right. I can do that using the next icons, move that across around the head, increase the distance if we're using gel pads, whatever it might be. So anyway, very flexible in where we can position everything, or very precise as well if we want to input specific coordinates. Yeah. Yes. Yeah, so that comes in the for those of you online, question about the specific distance of the focus. That comes into the table at the bottom here where we set that distance. Yeah, so if it's sorry, if it's a transducer with a fixed focal length, then that would be in the properties of the previous step, the file that we load for that transducer. If it's a steerable transducer, then we would use this table to, if I stand by this one, add sonication. One of the variables you can see here is that distance. Again, you may or may not know what that distance needs to be. There is some tools here that allow you to check that. So I can measure distance, say from exit plane or the back of the bowl of the transducer, whatever parameter you need to measure from to the target area, and that can at least give you an estimate of what you need to put as the focal distance, in this case, using a NeuroFuss system, let's say. Click again, so yeah, 39 millimeters for argument's sake. But yeah, as I said, if it's a fixed focal distance, then that's in the calibration file. A little bit easier to manage in that case. So let's say 39. So in this bottom table, I am setting my sonication parameters now. Frequency, that's been derived from the transducer that I selected. The amplitude, intensity, that can be defined in pressure or in ISPPA terms, and those two values are linked to each other. So if you change one, it updates the other. And then if I want to change the timing parameters, I edit this box and set my pulse duration, the repetition interval, whether I have a ramp defined, an amplitude ramp, and the duration of that amplitude ramp, and then if there are repeated trains as well. And then we can have multiple sonications as well. These can be linked to each other, or they can be independent from each other. So if you wanted to, for example, compare the output of multiple different transducer locations, you would do it as multiple points in this table and move the transducer each time. Or if you want to compare different focal distances, you can do that here. So one at 40, one at 50 millimeters, for example, and you can switch them on and off. But this table can also be used to link sonications together with the cooling time between them. So you can calculate the temperature profile that is induced in that target over the full session. So as a safety measurement. Last main thing I need to do before sending this for evaluation is to set my simulation window, if you like. You can see it's the white grid that's placed over the top here. If I click this button, it'll go to the minimum size required, which is just covering the transducer itself, so not particularly useful. But if you want to kind of start at the minimum and increase, just to give you the fastest result, because we're doing a trial and error process, trying to find the best position for everything. So I can just extend this out, make sure I'm covering at least my target area. And if the focus is not over that target area, you've missed anyway. So that's a location you don't need to persist with. Once all that's done, we click evaluate. That goes to currently the UCL server, but it will be when it's live using a cloud-based server, which means processing time is as fast as it can be, even when you are doing whole head 500 kilohertz or 1000 kilohertz frequency, 4 elements, and in the settings here, doing multiple grid points per wavelength. So 6 is a pretty good starting point. If we want to be a little bit faster, just need a quick result, we can go down to about 4. We can go even higher again if you want the best resolution possible. And you don't necessarily need to run the thermal simulation until you get to your optimized position for focus, for targeting. And then you run the thermal simulation in your final result to get the safety parameters. So you can save yourself a bit of time and a bit of computing units, which you get a generous amount with a K-Plan license for three years. And then if you need more, you can add more later or beyond the 3 years. Once that's done, you can then download the results. So I'll quickly go back now to some of those examples before passing over to Kyle. incidence angle. As I said, that's quite an interesting one to look at. So these are simulations that have been done already. This one being with a 500 kilohertz 2-element transducer. We go back to that planning page. This shows the last position of the transducer in these simulations. So it's the 40 degrees incidence angle. I can switch on the, let's see, the MRI. Yeah, no, maybe it's not included even. Okay. And go for, right, the pressure at 40 degrees, as you can see, as expected, pretty much bounce straight off the skull. No use at all. Come further down, 30 degrees. More in the skull, still lots bouncing off. 20 degrees, a little bit getting through to the cortex. 10 degrees, that's temperature, sorry. 10 degrees pressure, as we learned from Professor Butts-Pauli in the Brainbox Initiative workshop on Saturday. That's about the maximum allowable incidence angle that we can work with and still get transfer into the brain. And then nominal, finally, and the difference between those two, how much it can cause the position of the focus to move quite a considerable amount, especially when we're at depth, when we're focusing to the furthest position of the transducer's capabilities. Yeah, so actually the transducer image remains the same regardless of which one I switch on. It's just the position that it was for the last sonication parameter. But each one of these assumes the transducer position at the corresponding angle. Yes, it's the transducer that was moving. It's just for illustrative purposes to show how the angle can affect how much energy is delivered to the brain. We weren't aiming for a particular target in this case, but it does illustrate that how those parameters can have a big influence on whether you hit your target or not. That makes sense. Yeah. So as I said, we weren't aiming for a particular target. We just kept the transducer in the same place and changed the angle, which means, yeah, you're going to get a massive drift. You saw me click on it at one point there, temperature as well. So the temperature profile at nominal incidence, as you can see, that shows where the majority of the heating is happening. If I click on that location, or in fact, I can go there by right-clicking and going to the maximum, automatically jumps there, and you can see the value reported here. That's not a 37-degree increase. That's a 1.7-degree increase from 36, but not a huge amount in the brain itself. Pretty good. Another quick example to go back to, maybe on the focal depth. So different position of the transducer this time, still using the same average brain template. And we can see comparisons between different focal distances in this case for a CTX, not a CTX anything at all. It's 300 kilohertz, so that's one of the other default transducers available. So what we look like at 70 millimeters, again, I can right-click, focus on the maximum and see where that is. So it jumps to the right position. I'm going to go hunting around for it. We stay in that location and go to 60 millimeters, which is both on. Not a massive difference. 50, then we start to see the shift back to superficial depth. and so on. Hopefully you get the picture. Does anybody have any questions? Or online? I'll keep an eye out on the chat. Go ahead, Henry. The temperature profile, yeah. So that's possible in this cooling time. So that would give you your duration between sonications. That might be over several hours, depends if you have different experiments during the study, all based on the same transducer location. And you have the ability then in this part of the settings, link thermal simulations for multiple sonications. If that's ticked, then it daisy chains them on together. If it's unticked, it treats them as just separate individual sonications that you might just be comparing other parameter variables and those changes. It assumes no sonication during that cooling time. So natural properties, that's going to be based on some input data, some publication somewhere that I don't know of. Yeah. Okay, excellent. Thank you very much, everyone, for coming in and picking up. So our plan now for the second half was to kind of, well, one, give Kyle a chance to make up for my hashed sonic introduction yesterday, and also invite questions from you guys as to what burning questions you have about techniques, what the systems are capable of, what you might want to be able to do in the future. Do you want to come up here? Oh, for the online people, you will. So
So I don't know how long we have, but I'm open for questions. So Kyle Morrison with Sonic Concepts. So we make the NeuroFUS system, manufacture it, designed it, came up with these 6 configurations, 7 micro TX, so 1 per periphery, and then these other 2-channel, 4-channel transducers, depending on kind of real estate that you have around the skull. But yeah, I wanted to just see if you guys had any questions with technology, NeuroFUS specifically, acoustics, as much as I can help with, maybe follow-up questions with K-Plan. It's kind of a small group, but it's all yours if you have any questions. What was one of this, Marcus Kaiser's? Yeah, you could. Yeah, you could. You'd want to model it. You can use a fast lens or a slow lens, depending on what you want to reach. But yeah, that, it's a concave spherical bowl. So you'd fill that up and you'd want to figure out, what coupling of that bowl would go to the skin or hair and put that in your model. I know that Jean-Francois, you make lenses. I think the point is we already have a bowl. I'd almost prefer it that, you have almost a custom, so the piezo itself starts at 100 millimeters. If you want your average steering to be at 100 millimeter depth, then you actually construct the bowl that way. So yes, you can use lenses, but it's not optimal for how NeuroFUS is designed. If you had a flat aperture, you could use a plano concave surface, and you actually could steer the focus up and down with just making that spherical bowl in that fast medium, so metal or some other fast acoustic medium material. Let's see, yeah. Snell's law. So, you know, it's just a simple, I like to use just the simple lens equation, but you can get more complex. But I mean, if you're going to be using this with the skull, you have the same issues as what you have now. But yeah, it's really just accounting for that time of flight as the speed of sound changes. You know, it's going into a faster material before water. So you're going to get more on the outside, it's going to end up reaching the water faster than the apex of that concavity. So it's just all about sound speed. Yeah. Oh, okay.
Yeah, so there is a question on the chat. It was about K-plan, about multiple transducers. Could we model multiple transducers at the same time? So the answer to that is not yet. It is in the plan to do that. At the moment, you would need to position a transducer separately and run the simulation separately. But the idea is to improve on that in the future and be able to run them together. Marcus, did you catch the lenses?
What's that?
Need to model it. That was the quick answer.
Yeah, you wanna model it. Yeah, and then there's, you know, let's talk about metrology a little bit. The metrology is, you know, as Ellie said, very important, especially for these thresholds between safety and efficacy. And so, you know, that's why we made sure we pointed out this error in NeuroFuss now, and we found it based off of some of the, well, I wrote that technical paper, but it's really important, to her point, that we go through MPL directly. So you double the uncertainty if you go and reference a RESON from RESON or from ONDA or for precision acoustics. So you double the uncertainty, just go directly through MPL. You could even get the NeuroFuss transducers calibrated, you know, at MPL. And they can do all sorts of things like holography, projecting back to the surface, whatever it is. But I think that's the next step. And I think all of us vendors should adopt that requirement of reducing the uncertainty by having it traceable directly to NPL. So there's no amplification of uncertainty. Coupling, I don't know about coupling to the skull. One thing that was brought up was hair, you know, and we've always thought, well, you have the skull, what's hair, you know, but just keep in mind that, you know, radiation force balance is actually, I think, well, polar bear hair would be the best, but horse hair was actually a generic way of absorbing all the material. Hair is a very good attenuator and absorber of sound. And so, you know, you have surfactants, you know, to get around the hair and to almost liquefy the hair a little bit so that it's slippery. But the idea is try to get away from any bubbles in there. But there's people who are working on additives to coupling gel. You know, some people will argue that you should degas the coupling gel. But again, it will evaporate over time. So you just want to make sure that it's a single use application. There's other ideas on coupling. I mean, one thing I've wanted to do is try to get the acoustics into the skin. So you have asperity really. You're pressing a metal up against the skin and it finds a way through the hair and it reduces these impedance mismatching layers. I mean, you have your piezo, you have a face plate, you have aqueous gel, sometimes a gel pad, and then another aqueous gel layer, hair and skin, and then fascia and skull. I mean, you have so many layers there. If you can get directly to the skin using these ideas, you know, you might be able to get rid of, well, at least mute the audible effect is kind of the hope there. But anyways, I think having that gap, the impedance gap between piezo and the skull is a big issue. the skull is a very good it's a perfect acoustic matching layer, by the way, to PZT. It's the geometric mean, about what, 5.5 megarails. So if you could scalp, I don't know if scalp's the right term, but yeah, if you take off the skin and couple directly the skull, it may not be quarter wave, but you would actually use the skull as a matching layer. And you wouldn't have that reverberation in between.
Sorry, I think that what people might be struggling here is trying to understand the first order magnitude of the effects from hair versus skull versus everyone focuses on one thing because it's their topic of research, but people trying to use this in a practical sense. I don't think we saw up to date a general sense of how much are each of these steps actually affecting things. You know, we talk about skull, is it a binary mass? We worry about the skull density, we worry about the porosity, but if hair has a 5x effect on it, then the skull kind of isn't meaningful. But
right.
So does someone have a sense of how much each of these layers affects how much is being transmitted? Like we talk about hair, like hair was this a side mention today versus the skull, but is hair a bigger problem than skull?
Yeah.
And that we're just kind of ignoring it because no one gets a research grant to study it or something, but it actually has a big effect on what's really happening. Or
I think a lot of us are in that spot right now. We're trying to learn, and you know, K-wave can only get you, K-plan can only get you so far.
K-wave starts at the scalp, right? So we don't know.
Yeah, but you can add layers, but they're linear layers. You can't, it's hard to represent the hair, and you know, in reality, there will be gas in between, you know, so how do you delineate this? Yeah, and stratify.
But everyone here is worrying about what's going on, you know, in the thalamus or something.
Yeah.
And we're kind of ignoring all the stuff that's between the piezoelectric and the thalamus. I don't know, could someone do some paper studying these steps? Because it affects how it actually gets used in the real world, right?
I think you're right, but we're not neglecting the past to the thalamus and the hair. So the hair is not a problem per se. We published this paper with the 220 kilohertz and 7 kilohertz, 700 kilohertz device. And I can tell you, actually, when we sonicated through the hair at 220 kilohertz low frequency, the impact of the degassing of the water was more important than the hair themselves. But air bubbles are a safety issue, because if you have just one or two tiny bubbles, it will not affect too much the transmission of the beam, because it's only a very small fraction of the surface that is affected, but bubbles would resonate. So depending on your acoustic parameters, if somehow you were just behind the threshold for skin burns, then you would have skin burns only around the bubbles. So it's more a safety issue, I think, than an efficacy issue. And hopefully, of course, what we all hope for is that when we use the devices, it is at a power that is so low that even with a couple of bubbles, there should not be any risk of skin burns. But that's something we need to have in our mind when doing the test.
Thank you.
Yeah. To follow up on that, you know, there's subtleties like the piezo stack will be able to react to air bubbles, it being wetted or air bubbles. So the idea is if you measure electrical impedance, you can decide if there's air or not. If you baseline it to a, well, let's just say a linear free field water, and then you start decoupling it, so you start bringing it out into air. The idea is if you monitor impedance using voltage and current, you can shut down that element. And that's a really good safety mechanism that we have for safety and really detriment to the device.
Just throwing ideas around, is there a way to, can you measure as opposed to transmit? You know how like a diagnostic ultrasound, you fire a pulse, and is there a way of looking at, you know, fire a pulse and you look at the echo back, and if echo back is really short, you can assume it's a bubble and then, flag the user that, maybe there's a bubble or something.
Yeah, that's probably even a better way to do it,
something like
using
that.
that full secco. It's obviously the more elements you have, the better.
Yeah.
But yeah, the idea is the next step in a lot of this is to try to perform aberration correction. And you
Or at least an equivalent to an impedance, in EEG, you have an impedance check where you look at the impedance. But if you get a high enough echo back, you don't know where it is, but at least you might know, hey, you might want to look for bubbles or something.
it's smart enough to
Yes.
see change.
Smush,
and it shuts
smush
it.
a transducer around to try to work that bubble
I
out
mean,
or
this
something.
doesn't need to be, it needs to be a percentage of change. It
Yeah.
doesn't need to be calibrated. It
Exactly.
just needs to show, okay, I've changed enough. It doesn't need to be too smart. It just needs to know it's too much difference from it being well coupled.
Yeah.
Shut it down. Now, what's another topic? Maybe that's enough.
I guess I just broadly want to know if, what the sort of next direction is for you guys, what sort of technology you're looking at adding. I know there's a lot of problems to solve as it is scientifically and technically, but if there's any, hopes for the technology that you guys are developing that you want to share.
Top secret.
Yeah, okay. Yeah, Cape Plan is gonna be really good once it's implemented. I really do think we need to be smarter about how to be able to account for skew. Right now, I mean, NeuroFUS is just annular correction, but there is skewing going on. Having some sort of lateral directivity would be really good. The problem is you can't have one without the other. If you want to steer axially, if you really want to steer laterally and correct for skew, now you have a 2D array. And so it's making things more complex. I'm happy to make 2D arrays for different families of devices, but we haven't incorporated it into NeuroFUS yet because we're still learning. Let's get all these issues resolved with what we're finding and then figure out how we can correct in a different direction. So that's kind of our motivation right now. Let's get everybody kind of appreciating what's happening with sound through the skull. Give you a little axial correction, but to make a 2D array, I mean, you're complicating a lot. A couple other things we've developed are NeuroFUS Envision includes imaging. And so we've made peripheral devices that have 15 megahertz imaging, and then you steer these unfocused transmitters on top of that. And so it penetrates 4 to 8 millimeters, somewhere in there, for really high precision peripheral imaging. Right, so we're about 2.5 megahertz instead of talking about 20 or 250 kilohertz. So even for small animals, that would be really nice. Now we got to get our marketing together for that, but I mean, that's technology we're sitting on, and for the peripheral work, I mean, that would be really useful. Yeah, I think, a lot of people are trying to image through the skull. Not a lot, but, obviously you have limitations with resolution because in order to penetrate the skull, you need lower frequency. So some people are using 1 megahertz. And then some people are going through the temporal window. I've seen as low as, or as high as 2.5 megahertz imaging through the temporal window. Those are 2D arrays for monitoring the MCA. So, I think at some point it would be really good to start including imaging. I mean, it's just that real-time feedback. You'll never have the resolution of the MR, but it might enable some biomarker comparisons or, give someone an understanding of the proximity of the intended target in anything that's way. Okay.
Excellent. And unless there's any other questions, thank you again for coming and having a sit down while you had a drink and listening to us. If you want to catch Kyle or me for any one-to-one questions, feel free. We'll be here tomorrow as well. Thank you.